The purpose of a propeller is to convert the power delivered by an engine into propulsive thrust in order to propel an aircraft. This thrust is achieved by the acceleration of a comparatively large mass of air rearwards, thereby producing forward thrust. The acceleration applied is not large when compared with other reaction systems, but this has its advantages, not least of which is that it is very efficient. The propeller consists of two or more aerodynamically shaped blades attached to a central hub. This hub is mounted onto a propeller shaft driven by the engine. The whole assembly is rotated by the propeller shaft, rather like rotating wings. Like a wing, a propeller blade has a root and a tip, a leading and trailing edge, and a cambered cross-section whose chord line passes from the centre of the leading edge radius to the trailing edge. At the root area, where the section of the blade becomes round, is the blade shank, while the base of the blade, where any pitch change mechanism would have to be attached, is called the blade butt. Having stated that the propeller blade is an aerofoil, it would be logical to expect that the definitions relating to the propeller would be the same as those for the wing. They are as follows. The chord line is a straight line joining the centres of curvature of the leading and trailing edges of an aerofoil. The chord is the distance between the leading and trailing edges measured along the chord line. There are, however, other definitions which are peculiar to the propeller, and we must consider these. For instance, the blade angle or pitch is the angle between the blade chord and the plane of rotation. Blade angle decreases from the root to the tip of the blade because the rotational velocity of the blade increases from root to tip. For reference purposes, the blade angle is measured at a point 75% of the blade length from the root. Sections near the tip of the propeller are at a greater distance from the propeller shaft and travel through a greater distance. Tip speed is therefore greater. The blade angle must be decreased towards the tip to give a constant angle of attack along the length of the blade. The blade angle determines the geometric pitch of the propeller. A small blade angle is called fine pitch. A large blade angle is called coarse pitch. The geometric pitch is the distance the propeller would travel forward in one complete revolution if it were moving through the air at the blade angle. In flight, the propeller does not move through the air at the geometric pitch. The distance it travels forward in each revolution depends on the aircraft's forward speed. The distance which it actually moves forward in each revolution is called the effective pitch, or advance per revolution. The difference between the geometric pitch and the effective pitch is called propeller slip. The helix angle is the angle that the actual path of the propeller makes to the plane of rotation. Although it definitely has connotations with regard to the wing, angle of attack is also pertinent to the propeller. The angle between the blade chord and the relative airflow is the angle of attack, shown here as alpha. The angle of attack is the result of the propeller's RPM and the aircraft's true airspeed. Notice how the angle of attack changes as the prop RPM changes. A propeller must be able to absorb all the shaft horsepower developed by the engine, and it also must operate with maximum efficiency throughout the required performance envelope of the aircraft. The critical factor here is tip velocity. If tip velocity is too high, the blade tips will approach the local speed of sound, and compressibility effects will decrease thrust and increase rotational drag. Supersonic tip speed will considerably reduce the efficiency of a propeller and greatly increase the noise it generates. This imposes a limit on propeller diameter and RPM, and the true airspeed at which it can be used. Another limitation on propeller diameter is the need to maintain adequate ground clearance. To increase power absorption, several characteristics of the propeller can be adjusted. The usual method is to increase the solidity of the propeller. Propeller solidity is the ratio of the total frontal area of the blades to the area of the propeller disc. An increase in solidity can be achieved by firstly increasing the chord of each blade. This increases the solidity, but blade aspect ratio is reduced, making the propeller less efficient. Secondly, the number of blades can be increased. Power absorption is thus increased without increasing the tip speed or reducing the aspect ratio. However, increasing the number of blades beyond a certain number, say 5 or 6, will reduce overall efficiency. Thrust is generated by accelerating air rearwards. Making the disc too solid will reduce the mass of air that can be drawn through the propeller and accelerated. To increase the number of blades efficiently, contra-rotating propellers are used. That is, two sets of blades rotating in opposite directions on the same shaft. Due to its rotation, a propeller generates yawing, rolling, and pitching moments. These are due to several different causes, such as torque reaction, gyroscopic precession, spiral slipstream effect, and asymmetric blade defect. The majority of modern engines are fitted with propellers which rotate clockwise when viewed from the rear, so-called right-hand propellers. If then the propeller rotates clockwise, the equal and opposite reaction, or torque, will give the aircraft an anti-clockwise rolling moment about the longitudinal axis. During takeoff, this will apply a greater download to the left wheel, causing more rolling resistance on the left wheel, making the aircraft want to yaw to the left. In flight, torque reaction will also make the aircraft want to roll to the left. Torque reaction will be greatest during high-power, low-indicated airspeed flight conditions. Low indicated airspeed will reduce the power of the controls to counter the turning moment due to torque. Torque reaction can be eliminated by fitting contra-rotating propellers. Torque from the two propellers, rotating in opposite directions on the same shaft, will cancel each other out. A rotating propeller has the properties of a gyroscope: rigidity in space and precession. The characteristic which produces gyroscopic effect is precession. Gyroscopic precession is a reaction that occurs when a force is applied to the rim of a rotating disc. When a force is applied to the rim of a propeller, the reaction occurs 90 degrees ahead in the direction of rotation and in the same direction as the applied force. As the aircraft is pitched up or down, or yawed left or right, a force is applied to the rim of the spinning propeller disc. For example, if an aircraft with a clockwise rotating propeller is pitched nose up, the reaction occurs at 90 degrees in the direction of rotation. That is, a right yawing moment. Gyroscopic effect can be easily determined when the point of application of the imagined forward force on the propeller disc is considered. As the propeller rotates, it produces a backward flow of air, or slipstream, which rotates around the aircraft, as illustrated here. This spiral slipstream causes a change in airflow around the fin. In the case shown here, due to the clockwise direction of propeller rotation, the spiral slipstream meets the fin at an angle from the left, producing a sideways force on the fin to the right. The amount of rotation given to the air will depend on the power setting. Spiral slipstream effect can be reduced by any or all of the following: a small fixed tab on the rudder, the engine thrust line being inclined slightly to the right, or offsetting the fin slightly.